Yes. Okay, there we go. And let's. Thank you. What's that? Oh, how did I not mark that? Darn it. That was not very bright. Romina, I'll have to get back to you in just a little bit because I need to mark it. Sorry, I totally don't know how I missed it. Yeah. Okay, folks, we're going to talk about a couple of things on this quiz. Oh no. Okay, thank you. Okay. There we go. So, folks, I want you to be careful with your language because a reaction intermediate is not a product. So if in there you have said a reaction intermediate is a product, that is incorrect. Okay, it is a substance. It is a chemical species. If you want to tell me something about when, you can say that exists when, okay? Or you can say that it is formed in one step of a reaction mechanism. So watch out for language like that, because if you literally say it is a thing that it isn't, then that's not going to work. Similarly, for an activated complex is not a step. So I got it is a step. No, it's not. Is the time? No. Is the peak? No. It's not the peak. It exists at the peak on the potential energy diagram, but it is not the peak. Yeah? So watch out for that. Okay, so watch out for language that says something that is untrue. Okay? Similarly, if you were to do a mathematical sentence, sometimes I get people doing things like this in a mathematical sentence. They'll say, let's say I wanted to find, let's say I had, 5 moles of HCl times 1 mole of NaOH for 1 mole of HCl. And then they'll write 5 moles of NaOH. Is this a true statement? No. Why would it be 4 moles?
Oh, it's just.
Is that a true statement?
Probably. It sounds sweet.
Does it?
The HCl cancels out the moles of the.
Is it a true statement?
What are we looking for?
Okay, we are looking, you've done a calculation here. Is this calculation correct?
Oh,
Wow.
no, it is because the 1 mole doesn't become 1 mole.
Yeah, it is correct. I know what you all are looking at going, no, it's not correct, but it is correct. But what happens is, then people will say, I want to find the concentration. Is that still a correct calculation? Or actually, let's make it easier. Divide by 2 liters. Hello, come on in.
Toby?
Toby? No.
Toby?
No, Toby.
And Owen.
We have 2 Owens, Owen Campbell or Owen Gandy, but Owen Gandy's not here. And Owen Campbell is in the bathroom. Okay. Okay, so we agreed that this is a correct statement. Yes, mathematical statement. Okay, so let's try this. 5 moles of HCl times 1 mole of NaOH over 1 mole of HCl equals 5 moles of NaOH. We agree that's correct, yes?
Yes.
Okay. Is that correct? If I want to find the concentration. How many people like what I've written? How many people do not like what I've written? How many people have no idea what I'm talking about? That's fair. Okay, that's fair. If this is true, I can't be sticking other numbers in there and still have it be true. If this equation, an equation is balanced, yes? Like I've got, like this side is equal to this side. If I all of a sudden divide this side by 2, is it equal anymore? No. So when you're doing a mathematical sentence, you also have to be careful that you don't say things that are untrue. Yes? So these things are untrue. Verbal statements, like written statements, this is an untrue mathematical statement. You would have to do that on the next line. You would have to say concentration of NaOH is equal to 5 moles of NaOH divided by 2 liters, which is 2.5 molar. And you can see 2.5 molar is not the same as 5 moles. Yeah, they're different, so not equal. Okay, so watch out that you're always writing things that are true. Second thing I want everybody to watch out for, I did not write it on your paper, but you all need to learn how to write your lowercase and capital letters. Okay, what I would like you to do is I would like you to take a piece of paper or maybe somewhere on your quiz, and you're going to go like this, and then you're going to go like this and draw like what looks like a street. Okay, draw what looks like a street with a dashed line. Okay, let's go. If you're not moving your pen, you're not writing it. I want you to write it. Because your elementary school teachers have failed you, because apparently nobody cares anymore whether you can write properly or not. What does a lowercase k look like?
Oh, not that.
Lowercase k, does it go all the way from the top to the bottom, or does it go from the middle to the bottom? Does the line go like this for a lowercase k, or does the line go like this for a lowercase k?
I forgot.
It's the first one, okay? And then does the little this thing, does it go all the way from the top to the bottom, or does it go like that? Like the second one, okay? So K for kilo is a lowercase k, and the line should be taller than the little alligator mouth, okay? Or the less than sign, okay?
I just write it slightly smaller than the other one.
No, that's not how it works. This is not kilo. That's wrong. Okay? Now, J, capital J. Does it start here or does it start up here?
Oh. Yeah.
Capital J starts up here.
Oh, I have this little.
And you have the option of putting the bar on the top, but you don't have to. Okay? So if you want to write kilojoules, that's going to be kilojoules.
Oh, wait, what? It's not a lowercase j.
It's not a lowercase j, capital J. And capital J's don't go like this. That's not a capital J. That's a weird thing that doesn't exist. Okay? So I know it sounds picky, but if you go off to university and you're using the wrong symbols, your professors and your TAs are going to be like, what is wrong with you? Why did nobody ever teach you this? Right? Whereas I'm like, I'm not thinking what's wrong with you. I'm like, why did your elementary schools not like catch this at some point? Right? Because they should have. Okay? Now, if you are learning English as a second language and your first alphabet is not the Roman style alphabet, then you have every excuse in the world, okay? Probably no one ever did teach you that, so now I am teaching you that. And that's all that I wanted to like super point out for today. Did anyone have any questions from the quiz that they would like to go over? Does anyone have any questions from the review that they would like to go over? Do I have a 2026 or am I just 2025? Just 2025. Okay. Nobody? Okay, I'm going to print it to there anyway, because on Monday, I will expect you to have questions. Because your test is on, or not Monday, Tuesday, because your test is on Wednesday. Okay, and I don't want school copiers, I want OneNote. Print. There we go. All right, then, if we are not doing that.
Should
Oh.
you be like really picky about everything on the test?
Yes, I will be picky. So and if it says kilojoules per mole, you need to write kilojoules per mole, not just kilojoules. Go with what it says on your document. Okay. And let's just throw this in here. There we go. Okay. And now we move on to equilibrium. So we made it through 2.1. Were there any questions from the homework there? No, we're good. All right. We're going to talk today about stresses and shifts, although we've already mentioned them. This is on page 24. So, color is an example of what type of property?
Observable properties.
Observable, what's the other word we can use for that? Macroscopic. An observable property. At equilibrium, and remember we can abbreviate equilibrium EQM, macroscopic properties are what? At equilibrium,
There's no change. Or
macroscopic properties are, what's a word we could use to say there's no change? They are static or constant. At equilibrium, what two things are equal? Forward rate and reverse rate. And if you recall, we talked about the word stress yesterday. What is a stress to a system? It's where we change the conditions, yes, okay? So a stress is a change that we make to the conditions of the system. The stress will make the forward and reverse rates unequal. For the purposes of graphing, stresses are considered to be instantaneous. In other words, they take no time. And if something takes no time on a graph, it shows up as a vertical spike. So let's do, first of all, a concentration graph here. So we have the concentration in moles per liter. And we have time. And a rate graph, we have rate versus time. And if we start with our forward rate and our reverse rate being equal, that means that initially, are we at equilibrium or not at equilibrium? We're at equilibrium. And then at a time here, we're going to apply a stress. And in this case, actually, let's have a H2 plus I2 in equilibrium with 2HI. Actually, no. Do I want to do that one? No. I'm so sorry. If you need whiteout because I messed you up, I have some here. So sorry. Let's do 2NO2 in equilibrium with, yeah, I'm so sorry, and 2O4. And if my stress is an increase in NO2, concentration of NO2, at the time of the stress, if our stress is an increase in concentration of NO2, what will happen right at this time here to the concentration of NO2? It will spike up, and it's going to be a vertical spike because remember, it takes no time. Okay, so the NO2 is going to go straight up. That is our vertical spike. Stress is a vertical spike.
What about the other graph we didn't get?
Wait.
Oh.
Yesterday we were showing shifts, not stresses. Stresses are considered to take no time, okay? Because otherwise it makes the graphing really ugly if we make them take any time at all, okay? It's just to make the graphs look nice and tidy, all right? We can make stresses fairly instantaneous. Like if I had a container, you probably don't want to draw this, but if I had a flask and it had a stopper in it and it contained our brown gas, I'm making it red because I don't have a brown pen, yes, and we had our colorless gas, which I'm going to make green. Okay, there's our colorless gas. If I stress the system by taking a syringe with a needle on the end, this is the needle, and I stick it right through the rubber stopper, all the way through, okay? And we've got our little syringe here, and it looks like this. And we've got our plunger, right? And it looks like that. And we got that little thing that we push down on. You guys with me? Okay, good. Sometimes my drawings, I'm never quite sure. And let's say it contains a whole bunch more of the red stuff. Yes? You can go squish, and it takes about maybe 1 second to deliver the red gas into there. Yes? So that change is fair. We consider it to be instantaneous. It makes the graph pretty, okay? Because otherwise you'd have to be like, oh, it goes along and then it kind of goes up like this. And then it just makes everything messy and it makes it confusing. Yes? So we're just going to have it go straight up. Straight up. So stresses are vertical spikes. If we increase the concentration of NO2, what have we done to the forward rate? Chat with your neighbor about that. If we increase the concentration of NO2, does it increase, decrease, or stay the same? Let's vote on this one. We're going to vote either increase, decrease, or stay the same. Or you can do like increase, decrease, stay the same. That'll work too. And you can also vote, I don't know yet, which is also perfectly fair. 5, 4, 3, 2, vote. Yes, it is going to go up. The forward rate is going to go up. And because that is a stress, what should it look like on the graph? It should look like a spike. So that forward rate is going to go straight up. What happens to our reverse rate in that microsecond? Have I done anything to the concentration of N2O4? It just stays the same.
When we do a spike up, how do we show that? the spike forward.
Is the forward rate? In this case, I've shown it as a black line and I've labeled the forward as a black line. I've shown the reverse as a red line, but if you don't have two different colors, you can always say my reverse I'm going to do as a dashed line.
Or no, what I meant is like if the time continues on, how do you like?
Oh, what happens after that, do you mean?
Yeah.
Well, that's a very good question.
Yeah.
So the reverse rate in that moment stays the same. And James was just asking, what happens after that? Well, that's a very good question. What do rate diagrams do? If the two rates are not equal, what do they do? You know, we did it yesterday. I'm pretty sure we did, or did I only do it with the other block? Did we do the interpretive dance?
What's the interpretive dance? Oh.
Did we do that? What do rate diagrams do? Yes? We have to do it again because obviously you guys did not remember. What do rate diagrams do? Do it with me. Say it, and do it. What do rate diagrams do? What kind of a diagram is it? What does it do? Make your hands do it. No, it doesn't go up. It goes to the side. Yes, very good. Okay, so you can imagine what's going to happen here is that the forward rate is going to decrease because the forward rate is going faster, so we're using up reactant. So there are fewer collisions between reactant particles. The reverse rate is going to speed up because we are making product faster than we are using it, so there's going to be more collisions between product molecules, and eventually the two rates once again become the same and we reach our new equilibrium. So our new equilibrium is here. This over here is our old equilibrium. What's happening in between the old equilibrium and the new equilibrium? What do we say is happening? That area is not at equilibrium. That system is, it is under stress. And when it is under stress, what does it do? It shifts. So this area right in here, it's shifting. Hello. All right. Now, while we're here, we might as well figure out what happens to our concentration of NO2 after it spikes up. So let's think about this. We have now stressed our system, so the forward rate has increased and the reverse rate stayed the same. So what's going to happen to the concentration of NO2 as time goes on? This is how much we're using. This is how much we're producing. What's going to happen to the concentration of NO2?
Decreases because I've already used it up.
It's going to decrease because we are using it faster than we are producing it. So the concentration of NO2 is going to go down, and it's going to go down in the following fashion, and it is going to end before the original concentration. It's going to try to get down to the original concentration, but it won't quite get there. So it's going to go down, but it's going to flatten out before we get to the original concentration. I'm actually going to redraw that because I did a terrible job on it. That's marginally better. No, it's not. I'm going to draw the line part first, and I'm going to make this line better. Ay, ay, ay. Well, that's the other thing you guys need to do. You need to work on your drawings for your kinetic energy diagrams, because they're not proportional. Like, they just look weird, right? Like,
Are you gonna be picky?
no, probably not, but
Because like
you should get good at, you should work on that. Do you know, like, it's a skill that you should work on. I'm probably not going to get any more picky than I was on the quiz.
oh,
Okay? All right, so that's what it would look like. Now, if we are using up NO2 faster than we are using it, what about N2O4? Are we making it faster or using it faster? N2O4, are we making it faster or using it faster?
make
We are making it faster.
because we're making NO2.
Yeah?
Or it produces N2O4.
Yeah, so we're making N2O4 faster. So that means N2O4 concentration is going to go higher. Now the question is, by how much?
Will it get to like the original concentration of NO2?
We got a 2 there. We've got a, well, there's no 1, but there would be a 1
Yeah.
if we had a coefficient. So if we use up this much NO2, comparatively, how much N2O4 should we be making?
Of that.
Pardon me?
Half of that.
Half of that, right? Because for every 2 NO2, you only make 1 N2O4.
The ratios again.
Yeah, so if this is going to be a 2x value, that little line there, then this is going to go up by 1x. Now, if this all felt like a lot of information hit you in the head at the same time, don't worry, we're going to slow down on this, but I wanted to kind of give you a flavor of everything before we get right into it. So just feel the flavor right now, taste the flavor, you know, kind of feel it out. It's okay if you don't understand it right now, all right? And now we're just going to talk about what things can be stresses, okay? So things that can be stresses. Concentration is a stress. And we just looked at that. We changed a concentration. We injected more of that brown gas. So that is a stress. We can change the volume of the container. That will change the pressure. That's a stress. Nathan, I have a quiz to give back to you. Somewhere. Okay, so we can have a change in the volume of the container, which will change the pressure. So for example, we might have a container that's this big. There's 8 gas particles in it. What if we made it really small?
With the same amount of particles,
With the same amount of particles.
the pressure will be
The pressure is going to be higher. What's going to happen to the number of collisions?
higher.
The number of collisions will increase. And if we make it bigger, what will happen to the number of collisions? The number of collisions will decrease. And we'll look at how specifically that affects it later, okay? Because it gets a little bit complicated depending on the number of gas molecules in the reactants in the products. But that's the general idea. If it's changing the number of collisions, the frequency of collisions, it's going to be changing the rate. And if it's changing the rate, it's probably changing the position of the equilibrium. And of course, we know that temperature changes rate. So it's going to change the position of the equilibrium. Now, things that are not stresses. Adding a catalyst. Adding a catalyst speeds up both reactions the same amount. So we might go from this, which is our original equilibrium, to this. Stop making it one line. Thank you, Microsoft. It just goes straight there. It's still the same equilibrium. It's just going back and forth faster.
So the graph will change.
So the graph will, the concentration graph won't change. The rate graph will change. So if we were to draw a rate graph for a catalyst, it would look like this. So there's our forward and our reverse rates. And what will happen is that, remember, it speeds up the forward and reverse rates the same amount. So if it speeds up the forward rate this much, how much does it speed up the reverse rate? The same amount. And if they're in the same place, how much shoo is there? There's no shoo. They're already there. They're just like, oh, we're still the same. We're just both faster now. Right? They don't have to come together because they already are together. And at this point, this is where we added a catalyst. And to be honest, it is exactly the same thing with surface area. Surface area speeds up the forward and reverse rates the same amount because there is more surface for anything to deposit on it. There is more surface for things to come off. It speeds up forward and reverse exactly the same. And if you remember, what does adding an inert gas do to rate?
Nothing.
It does not change rate, therefore it does not cause a shift. It's not a stress.
Is it because inert gases usually don't form bonds?
They never form bonds.
No,
That's the whole purpose of an inert
no, but
gas.
like
Oh, yeah, but you gotta like do crazy things. Yeah, xenon tetrabromide or whatever, yeah. Okay, but that's not gonna happen in a chemistry lab in the high school situation, okay? Does not affect rate. So therefore, it's not a stress. What does inert mean? Unreactive. Okay, and this is just to see if you can remember them from the previous page. So flip the page and see if you can remember them without looking. Can you remember it from 10 seconds ago?
If we don't write change in, they write wrong.
That's okay. No, it's fine. Okay, so things that are stresses: concentration, temperature, volume, pressure. Things that are not stresses: catalyst, surface area, adding an inert gas. So concentration, temperature, and pressure, volume, they make the forward and reverse rates temporarily what?
I don't know, like
What would make it shift?
unbalanced.
Unbalanced, yes, unequal. Unbalanced would also work, okay? Unbalanced would also work. And they can either do this by changing only one of the two rates. That's what happened when we added the NO2. We only changed the forward rate. Yes? Or perhaps you change both rates.
So one more than that.
Yes, but by different amounts. So the factors that change only one of the two rates, that would be concentration, and the factors that change both rates would be temperature and then pressure, volume. It's going to depend on whether you have gases in the reactants or the products or both. And in fact, sometimes if you change the pressure and volume and you've got the same gas molecule, number of gas molecules in the products and reactants, it actually doesn't cause a shift. So it's not a stress. So we're just going to look at concentration and temperature as things that for sure make a change. Okay? So things that are not a shift, that are not stresses, they leave the forward and reverse rates. So if it is not a stress, they leave them equal.
Or the same.
Or the same, yes. They either do this by increasing or decreasing rates the same. I guess I should have left room for amount because that would be better grammar, but we'll let it be. The factors that do this are surface area and catalyst. I don't like this page. I need to redo this. Or by not changing either rate at all. And what doesn't change either rate at all? Inert gas. So we've talked about all the things that are stresses. Now we're going to talk about how things shift. And we've already looked at it on page 1, but now we're going to look at it here. Okay. So let me just see what I decided to do here. What did I actually use as my example here? That's a good question.
You just drew. I believe I looked at it by accident. You know, like it's a show.
Yeah, this was NO2 and N2O4. So let's do this like this, where we have N2O4 in equilibrium with 2NO2. Now I've drawn it the other way around, I think. Did I draw it the other way around before? It doesn't matter. You can write it out either way. Okay, so on our x-axis, we're going to have concentration in molar. And we got NO2 and we've got N2O4. And let's say the stress this time is an increase in the concentration of N2O4. What should that look like? N2O4 will do what? It will spike up. We get a vertical spike.
On a concentration graph, you don't want to put them too close together to the line.
I mean, you can just make sure, like, if you had drawn them closer together, you would just make your spike smaller. Yeah? Yeah, so it's kind of good to leave a little space in between them. And now what's going to happen? Have a chat with your neighbor. What will happen to the NO2 right now? Is it going to have a spike? What's going to happen once it starts shifting? Because we always have a stress and then we have a shift. What is this graph going to look like now? So have a chat with your neighbor about that. What's going to happen?
Just like that.
Yeah, no, yeah, it will eventually, but I don't think. Oh, no, it will go double the amount. It's just gonna go down. It's gonna be like. I was going down.
Then it's like touchy touch. So like that. I'm sorry.
No worries.
Yeah, it'll be something like that. I'll like the graph.
Okay,
Like that. There's text.
so we've had our stress. What comes after the stress? Shift. Are shifts vertical or gradual? They are gradual. All right, so we're going to have our shift. And what's going to happen to the concentration of N2O4 at the beginning of the shift while we are going forward faster than we are going backward? N2O4 is going to go down. Where should it end?
Like double the amount.
Where should it end? Here, or here, or here, or here? Pick one of those. Do you like number 1, 2, 3, or 4? 3 is right at the line. Does it go back to exactly where it started?
No, usually not. No, so probably like.
Not even just not usually, never. It never gets back to where it started. Does it ever go past where it started? No, it never goes past where it started. It tries, you can think about it, you can personify it, okay? It doesn't really try to do anything. It tries to get back to its original concentration, but it doesn't quite make it, okay? We'll look at mathematically why later in the unit, okay? So, whatever one was stressed will try to get back to its original concentration, but it doesn't quite make it.
The NO2 will go down along with it to the same place.
To get? To get's not one word.
I mean, like.
Hang on. Okay. What will happen to the concentration of NO2? Is it going to go up or down or stay the same? Are we creating more of it? Are we using it up, or is it staying the same? We are creating more of it because that yellow forward arrow is bigger than the backwards arrow. So we are making more of it. And it makes sense. If we are using up N2O4, we must be making NO2. Yes? So we are using up N2O4. That means we must be making the other thing, because the reaction's shifting to the right. And that means our concentration of NO2 is going to go up. By how much does it go up?
Double.
Yes, by double. So what we can do is we can say, okay, this amount, we're going to call that X. This amount, I'm going to hope that I do twice as much. But if I don't quite manage it, as long as I label it 2X, then I can be like, it's supposed to be twice as much.
So that one doesn't spike up.
No, that one doesn't spike because you didn't stress it.
Oh.
Our stress was just an increase in N2O4. And things I want you to notice about the curvy part of the graph where we're shifting. At the beginning of the shift, is that steep? Is that shallow? What's happening to the rate? Is that a steep slope or a shallow slope? Steep. And then it becomes more shallow. And finally it becomes flat. Same thing with this one down here. It starts out steep. Dear God, I'm writing too much on here. Maybe I won't label it here. Maybe we'll label it somewhere else. It too goes steep, shallow, flat. Okay, the graphs, the changes during the shift are always steep, shallow, flat. Okay? And it actually says it over here. It goes steep, number 1, steep, number 2, shallow, number 3, flat. So here is a rate diagram. And what I'd like you to do is I would like you to label the old equilibrium, the stress, and the new equilibrium. In your diagram, can you actually see the difference in the lines? Or do they look the same?
It's just slightly thicker.
They look the same? Okay, so I need to fix it. Okay, that's all right. You can look up here and you can look and say which one is red and which one is... So this one here is forward. Yeah, the top one is forward. The bottom one is reverse. I need to fix that. Fix. And then once you've done that labeling, you can answer the other questions. So check with what I've got written up here to see if you've got your old, new, and shift correctly labeled. I mean, it doesn't have to look exactly like that. If you chose to circle the shift or something or highlight it, that would also be fine. the moment of the stress, what happens to the forward and the reverse rates?
So,
The forward rate does what? Forward rate goes up. What happens to the reverse rate?
it starts to go. Gradually that goes up.
It does nothing. Not in that instant. Okay? Does nothing. Not at that moment. Are the slopes at the beginning of the shift steep or shallow? Steep.
Wait, it's always.
Always. It always goes steep, shallow, flat. And if the curve is steep, what does that mean about the change in the rate? Is it changing slowly or is it changing quickly? It is changing quickly. So the rate of change is quick at the beginning. Are the slopes at the end of the shift steep or shallow? Shallow. Okay, and that means that by the end of the shift, the rates are changing slower, slowly. Let us try sample problem number 2, and I think that'll take us till all we can get done for today. Label the old equilibrium, the stress, the shift, and the new equilibrium.
That means. What should I do? Why?
Are you guys good with the old equilibrium, stress, shift, and new equilibrium? Okay, this means that at the are the slopes at the beginning of the shift steep or shallow? Steep. So does it matter whether it's a concentration diagram or a rate diagram in terms of the shape of the shift? No, it's always going to be steep, shallow, flat, no matter whether it's a rate diagram or a concentration diagram. So it's going to be steep. That means the concentrations are changing slowly or quickly. A steep slope is a quick. And at the end, shallow. And that means the concentrations are changing slowly. Concentration is an example of what type of property?
Microscopic property.
A what kind of property? Macro.
But we can't see the concentration.
It's a property that doesn't change, therefore it's macroscopic. And if it is a macroscopic property, what do we know about it at equilibrium? It is, sorry? Constant, yes. So this whole steep, shallow, flat, never mind, we'll talk about that tomorrow. Okay? Your homework this weekend, what is it?
Study for the test.
Study for your test. If you leave your studying till Tuesday, then you are going to do poorly. I can just guarantee you. And you know what? If you do poorly and you come to me and you say, Miss Spence, how can I make my grade better? Can I rewrite the test? What will I say? No. If you say, I'm not ready for the test on Wednesday, what will I say?
No.
Too bad. Unless, you fall ill over the weekend and you're like vomiting up a lung or something, right? And if you did really badly and you're like, what can I do to change my mark? You won't let me write the test. It's the end of semester. I don't know what to do. I will say, invent a time machine. Go back and study for the whole weekend. Don't just study on Monday. Don't just study on Tuesday. Study at least a portion every day on the weekends. Okay? Every day.